Before we look at the quantum aspect or the particle aspect of light, let's just review a couple things about the wave properties of light because they still apply. For example, if we consider just the little narrow region of the electromagnetic spectrum that we can see, the visible spectrum, then we can see light anywhere from about 400 nanometers wavelength to 700, and that corresponds to, a purple light up into a red light. And if we imagine the wavelengths, we've got a really short wavelength, and then as we get towards the red, those wavelengths are getting longer and longer. So wavelength increases in this direction for visible light towards red. But remember, the wavelength is tied to another wave property called the frequency, and what pulls those two properties together is the speed of the wave. So the velocity of the wave, v, is equal to the wavelength times the frequency, and for all electromagnetic radiation, light and radio waves and microwaves, they all travel at exactly the same speed, and we use the symbol c, and that's the c in Einstein's E equals mc squared, and the speed of all light is 300 million meters per second. So looking at this relationship, it tells us that if the wavelength increases from violet to red, then the frequency of the light must increase in the opposite direction. So in other words, red light may have the longest wavelength, but the longest wavelength has also the lowest frequency. Where does electromagnetic radiation come from? Well, it comes from the excitation of electrons within an atom. So consider the diagram here, and this represents a very simplified view of an atom with electrons. I'll put two of them here, this one and this one, which exist in their ground state. And the ground state is just the original non-energized state of an electron. And electrons, when they absorb energy, can jump to excited states. So let's take, for example, this electron here, and let's say that electron absorbs energy, and that energy could come in the form of heat or being bombarded with some other kind of particles or even being bombarded with other electromagnetic radiation. And let's say that electron jumps from the n equals 1, or its ground state, to the n equals 2. Well, the problem is that electron's not stable there, and it doesn't last very long. So it very quickly falls back to its ground state. Now, what happened to all that energy that it absorbed? It now has to be released. And the way that it's released is in the form of what we call a photon of light. So that photon maybe represents red light, whereas perhaps over on this side of the atom, maybe this electron absorbs enough energy to jump all the way out to n equals 3. Now, electrons can't exist anywhere other than these discrete energy levels, and we'll get more to that later, but if this electron absorbs enough energy to jump all the way out to n equals 3, then it can fall all the way back down to its ground state. And since that required more energy, so it's going to release more energy, then the photon of light that we see coming off of that jump is going to have more energy. Maybe we see it as a different color altogether. So Max Planck is the first to really theorize about this concept of energy being given off by these electrons jumping around. And not only energy, but energy being given off in very discrete, quantified amounts. And that's where this whole term quantum theory originates from. The quantum part of quantum theory deals with that very specific quantum of energy that's given off. And we call that quantum of energy a photon. It's like a small packet of energy, very discrete, very specific, that has everything to do with the amount of energy absorbed and then released when electrons jump back and forth between energy levels. Planck also was able to define that the energy of one of these photons is equal to some constant, coincidentally Planck's constant, times the frequency of that photon. Planck's constant is a very small value, as you would expect, because we're talking about the energy of just one single photon here. So that Planck's constant is 6.63 times 10 to the negative 34th, and the units there would be joule seconds. So let's review the outcome of the photoelectric effect. When incoming photons strike the surface of a metal, as long as the energy of those photons is sufficient, electrons can be then ejected from the surface of the metal. So those incoming photons have an energy, according to Planck, HF, and those outgoing emitted electrons, these are called photoelectrons, have a maximum kinetic energy of 1/2 mv squared. So one other piece of energy that we have to consider, though, is that the property of the metal itself. So electrons can't just easily escape the surface of a metal. It takes a certain amount of energy just to break free of the surface. And we call that minimum energy to release the electron the work function of that particular metal. And the symbol for that is the phi. And phi is equal to the work function. So when we put these things together, it's just an expression of the law of conservation of energy, that the incoming photon energy is equal to the work function of the metal plus the maximum kinetic energy of the outgoing photoelectrons. So if we look at this, it makes sense that the only way electrons can be detected coming off of that surface of the metal is if the incoming photon energy is at least as large or greater than the work function of the metal. If we plot a graph of the kinetic energy of the outgoing photoelectrons versus the frequency of the incoming photons, then we get a graph that should make a lot of sense. Because if you go back to our original derivation of the photoelectric effect, which said, remember, that the kinetic energy, and we rearranged this a little bit. Remember, we'll write it in the original version, that the energy of the incoming photons is equal to the work function plus the kinetic energy of the outgoing electrons. We've just rearranged this to look like a linear equation, y equals mx plus b. So the kinetic energy is directly proportional to the frequency of the incoming electrons, but what's important and what you should recognize here is that the kinetic energy of the electrons leaving the surface of the metal, we don't see any kinetic energy until we've reached that minimal frequency, and we call that the threshold frequency, the minimum frequency. If we don't have a frequency of light at least equal to the threshold frequency, then we haven't yet reached the work function of the metal. If we trace our line back and we look at, and that's looking up at the equation, this is just the y-intercept. If we trace this all the way down to the negative y-axis, well, then that's going to equal our work function. And if we look even closer at the graph, then we can see that the slope of this graph, if we plot y equals mx plus b, and it's a minus b here, that the slope of this graph is equal to Planck's constant. So I could find the maximum kinetic energy of these photoelectrons if I could somehow convert it into potential energy. And that's exactly what we do in order to find that energy. Because if I put negative charge on my collector plate, just the right negative charge, then these electrons, these photoelectrons, will be repelled by that plate, and I can convert my kinetic energy of my photoelectrons into potential energy at the plate. So we apply a voltage across my collector and my emitter plate, which means I just, almost like a capacitor, I've got two oppositely charged plates. So as those electrons travel towards the collector, they're going to slow down and slow down and slow down and slow down until all of that kinetic energy is now converted into the potential energy. And remember, the potential energy of an electron in an electric field of voltage V is Q times V, and we call that voltage specifically the stopping potential. So that's a new term. We can calculate the stopping potential as the voltage that's necessary in order to stop these photoelectrons traveling with that maximum kinetic energy. If we can fine-tune and know that voltage, then we can easily then calculate, because Q would just be the charge of an electron, we can then just easily calculate the velocity of those incoming photoelectrons.